Let's start with paper 8. Question number 1 in paper 8 says the amount of charge required to electrify a sphere of radii. So radius here is 2 centimeter. Let's make it 2 into 10 to the power minus 2 meters. So as to get surface charge density, be very careful. Sigma is denoted as surface charge density, and that is given here as 4 upon pi coulomb per meter square. So coulomb m to the power minus 2, right? Now this is the given data. They are asking what? Amount of charge. So Q is unknown, right? Let's recall our formula for sigma. Sigma is nothing but charge per unit area, right? And whose area? Sphere. What is the area of a sphere? Be very careful, it's not pi r square. That's for a circle. So area of sphere is 4 pi r square, right? So let me write here sigma is equals to Q upon 4 pi r square, right? And let's cross multiply. So on cross multiplying, Q will be equals to sigma into 4 pi r square. Now what is sigma here? Sigma here is 4 upon pi into 4 pi into r square. What's r? 2 into 10 to the power minus 2 into 2 into 10 to the power minus 2, right? Now let's simplify it further. 4 pi and pi cancels. We left with 4 4s are 16 and 16 into 2 32, 2s are 64. 64 into 10 raised to minus 4 coulombs. That's your answer. Is there any option? Yes, option C is the correct answer for question number 1. Let's move to question number 2. If a charge is given to a sphere of radii 1 meter, so radii here is 1 meter and Q is equals to how much? 88 coulombs. And what we are talking about? Sphere. So if the charge is given to a sphere of radius is 1 meter and that is 88 coulomb, the surface charge density of the sphere must be. So we have to find sigma, that is equals to Q by area. Okay. So sigma is equals to Q by area. Correct. Now what is Q? Q is 88. Okay. And area is 4 pi r square. So 4 into pi into r square. R is what? 1. 1 into 1 you can make it, right? 1 into 1 is 1. Okay. So this will be here 88 upon 4 into 22 by 7. Okay. 1 into 1 is 1. So let's move ahead. 22. 11 8s are 11 2s are and 4 2s are 8 cancel 7. 7 coulomb per meter square. Okay. And that will be your correct answer, option A. This was question number 2. Let's move to question number 3. So question number 3 says if the charge present across 1 meter, so R is given here as 1 meter of a uniformly charged wire, be very careful, this is length, not the radii, because it's a wire and not a sphere. So if the charge present across 1 meter of a uniformly charged wire is 20 coulombs, the length across which 35 coulomb of charge is present will be, so you have Q dash which is equals to 35 coulomb. Now always remember, if there is a wire, then one parameter will remain same if it is a uniformly charged wire. What is that? Lambda. What is lambda? Linear charge density, and that is charge per unit length. So let's first find lambda. So lambda will be equals to how much? Q, which is 20 upon 1, which is 20 coulomb per meter. This remains fixed. So if the charge is changed, if across some part of wire, let's imagine it like this. If this is a wire and one part of wire is this section, in this section, what is the charge? 20 coulomb, right? And what's the length? 1 meter. Now they are saying in this section of wire, the charge is 35 coulomb. What will be this length? So what is fixed for both sections? Lambda. So lambda in this second case will be Q dash upon L dash, right? I have not made lambda dash. Why? Because lambda throughout this wire will remain constant. So L dash will be equals to, what is Q dash? 35 upon lambda. What is lambda? 20. Correct? So let's cancel out it. Okay. And we left with 3.5 divided by 2. Okay. So this will give you 2 1s are 2 and 15 to 1.75. Okay. Meter. That will be the length. So correct answer is option B. I hope you understood. Clear it is? So what remains constant across a wire? If it is a uniformly charged. If it is not uniformly charged, then lambda will not remain same, because at different sections, different amount of charges are present, right? Let's move to next one. If the electric field vector E is given by this, the flux through the surface area of 40 units in XZ plane. Okay, now be very careful. Let me write here what is given first. So electric field here is given as 3I plus 2J minus 5K. Area is given here as 40 units, and be very careful, this is very important, in XZ plane. Now we know that when we use this equation, okay, electric field E into area, there is a small vector which we call as normal vector. So here the normal to the area will be in which direction? Normal means perpendicular. If XZ is the, so if this is a room, let's say this is the room in which you are sitting right now, okay, and here this is our x-axis, this is our y-axis, and this is our z-axis, right? You can look around and see x-axis, you can decide any one as x, y, z. Now if this is our xz plane, this wall is our xz plane here, and then which direction is perpendicular to it? Y-axis, right? So this area will have a normal in y-axis. So this will have 40, we will write it as 40 j cap. Why j cap? Because of xz plane. So sir, you mean if it was yz, then which one will be here vector? I cap, because x-axis will be perpendicular to yz, right? And so on. So here area is 40j. So what will be our flux? Our flux is phi, which is equals to E into area, okay, and n cap. This n cap is this j, correct? So electric field is how much? Electric field is 3I plus 2j minus 5k cap. And area is 40 j cap, right? Now let's multiply both. So this will be how much? See, it's a dot product. So for a dot product, I cap and k cap, there is no corresponding vector, so they will cancel out. Okay, 0, 0. Only j cap will be multiplied. 4 2s are 80, and j dot j is 1. So 80 units. That's your, okay. And what's the units of flux? Electric field is Newton per coulomb. So Newton meter square per coulomb. Okay, if you want to specifically write. So it is 80 units. That's the correct answer for fourth one. Let's move to fifth one. Question number, okay, great. Quite similar to the previous one. If the electric field vector E is given now, E as our 3I plus 2J minus 5K cap. Now quite similar. See here. Area is also same, 40 units only. Okay, but here it is YZ plane. So which axis is perpendicular to YZ? X axis. So this will become I cap. Okay. To clear the concept, we have kept the same question, but only changed here instead of ZX. Okay, we have placed it YZ. Okay. So here 40 I cap, and now if I find the dot product of both, this I cap will be multiplied only with I cap if you know the basic dot product. Okay. So 4 3s are 12, 120 units. So that is our option B. Let's move to question number 6th one. If the electric field vector is given by this much, okay, now it is XY plane. So that was the left part, but here they have changed the area also. So electric field here is minus 2I plus 2J and plus 4K cap. And what's the area? Area is 10 units. And 10 units in which plane? XY. So which one is perpendicular? K cap. K cap Y, Z axis is perpendicular to XY plane. So now when you multiply, the flux phi will be equals to, only multiplied with that, it will be 40 units. Why 40? Because 10 is multiplied with 4 only, I and j. There are no components to use, okay, for dot product. Okay, let's move. Which one is the correct option? B. Let's move to question number 7. A square plane sheet of side length 7 meters. So there is a square sheet here, okay, and each side is 7 meters. So I am writing here A is equals to 7 meter. Is placed in a uniform electric field. E is equals to 2 into 10 to the power 4 Newton per coulomb, making an angle of 30 degree with the field. So theta is 30 degree. Listen very carefully. This angle is between the electric, let's say the electric field is going like this. So the angle between the sheet and this is 30 degree. If the sheet and the field is making 30 degree, where will be the normal? Normal of the sheet will be perpendicular to the sheet, right? So angle between electric field and the normal will be 60 degree. And we have to take this angle. So let me write here angle between, because we always take for this angle between the normal to the field and normal to the area and the electric field. Correct? Great. So this will be theta equal to 60 degree. You have to take into account here, not 30 degree. Okay. The electric flux you have to find. So electric flux phi will be equals to EA cos of theta. So electric field is given how much? 2 into 10 to the power 4. Area of this sheet will be, it's a square sheet as per the question. So area will be side square. So into 7 and cos of 60 degree. Be very careful. Cos of 60 and not 30. So into half. So this will become 2 and cancel. 7 7s are 49 into 10 to the power 4 units or Newton meter square per coulombs. 49 into 10 to the power 4. Is there any such option? No. So 49 into, let me read the question once again, or we have, so a square plane sheet of side length 7 meter is placed in a uniform electric field making an angle of 30 degree with the field. Okay, the electric flux you have to find. So correct answer is option D, none for this. Clear? Always remember, you have to take the angle between the normal to the area and the electric field and not direct the angle between the field and the area. Okay, let's move to question number 8. The total number of electric field lines coming out of 885 coulomb of charge is, so we'll directly use here Gauss's law. What is Gauss's law? Flux phi is equals to charge upon epsilon naught. Okay, electric field lines, number of electric field lines is flux. So that will be Q. What is Q? 885 and whole divided by 8.85 into 10 to the power minus 12. Let's remove this point. You will get here 100. This cancels with this and you left with 100 into 10 to the power minus 12. So correct answer is 10 to the power minus 10 units. Okay. 10 to the power minus 10 is, plus. When it goes on the top, it will become plus here. Okay. So this will become, instead of 12 plus, if it is becoming, then it will be 10 to the power 14 units. Okay. So the correct answer is option B. Be very careful with the powers. Okay. This was 8th one. So this will be, let's move to 9th one. 9th one says a square plane sheet of side length 2 meters. So here A is 2 meter is placed in a uniform electric field E with 2 into 10 to the power 4 Newton per coulomb, making an angle theta 0 degree with the field. 0 degree with whom? Field. The flux we have to find. Clear it is? So here if it is area, this is area and it is making 0 degree, which means electric field is along the normal. What is the angle between normal and electric field? That will be 90 degree. Okay. A diagram, this is like this. 0 degree will be this. Okay. This is electric field and this is normal here. Sorry. So theta is 90 degree between them. Okay. Because electric field is along the sheet. Okay. Not perpendicular to the sheet. So theta will be 90 degree and flux phi will be equals to EA cos 90. Cos 90 is 0. So directly straight away everything becomes 0. Option B is correct. Let's move to the last question of paper 8. The total electric flux coming out of a charge Q is equals to 10 to the power 4. Okay. Wait, total flux is given, not the charge. So flux phi is 10 to the power 4. The charge must be. So we will again use Gauss's law. Flux phi is equals to Q by epsilon naught and Q will be equals to flux phi into epsilon naught. Flux phi is how much? 10 to the power 4 and epsilon naught is 8.854 into 10 to the power minus 12. So this minus 12 and that will be 8.854 into 10 to the power minus 8 coulomb. That's the charge. Option A. This was paper 8.